Find the pore water pressure at point B in kilopascals. In this problem, an aquifer sits below a 3-meter thick layer of silt, which sits below a 2-meter thick layer of sand, upon which a body of water of unknown depth, x, resides. The hydraulic conductivities of the sand and silt layers are given. Points A, B, and C are positioned at the layer boundaries, and point D is at the surface of the water. A well pump pumps water from the aquifer, which holds the pore water pressure at point A to 24.5 kilopascals. This pumping causes the flow of water downward through the soil profile at a given seepage velocity, v. The pore water pressure at point B is equal to the density of water times the acceleration from gravity times the pressure head at point B, where the density of water is 1 megagram per meter cubed, the acceleration from gravity is 9.81 meters per second squared, and the pressure head at point B still needs to be computed. At this point, it may be convenient to tabulate the head values for points A through D. This includes the total head, the elevation head, and the pressure head. Since we neglect velocity head, the total head equals the elevation head plus the pressure head. We assume a vertical datum at point A to equal 0, so we assign point A to have an elevation head of 0 meters. Since the silt layer is 3 meters thick, point B has an elevation head of 3 meters. Similarly, since the sand layer is 2 meters thick, point C has an elevation head of 5 meters. Since the depth of water is x meters deep, the elevation head at point D equals 5 plus x meters. Next, let's look at the pressure head values and define atmospheric pressure, also known as gauge pressure, to 0. So the pressure head at point D is 0 meters. Since the water is x meters deep, the pressure head at point C is x meters, and we currently don't know the pressure head at point B, so we'll simply write in H sub P comma B in the table as a placeholder. We don't know the pressure head at point A either. However, we were given that the pore water pressure at point A is 24.5 kilopascals, and the pressure head can be computed by knowing the pore water pressure. Plugging in our values for the pore water pressure, the density of water, and the gravitational acceleration, we compute the pressure head at point A to equal 2.5 meters. Remembering the total head equals the elevation head plus the pressure head, we can compute the total head values for points A, B, C, and D. Next, we'll find the relationship between the total head at point B and the depth of water, x, based on the principle that the flow rate through the sand layer is equivalent to the flow rate through the silt layer. Let's refer to the sand properties as CB, meaning between points C and B, and the silt properties will be BA. So we have Q sub BC equals Q sub BA, where the flow rate for each layer is the hydraulic conductivity times the gradient times the area. Since the cross-sectional area will be the same for both layers, they can cancel out of the equation. Now, we're left with the hydraulic conductivities, both of which we've been given, and the gradients. The gradient is the total head loss divided by the length over which the head loss occurs. These lengths correspond to the layer thicknesses, which we've been given. We also notice the total head values, which we still need to determine. If we solve the equation for the total head at point B and plug in our values, remembering that we already solved for the total head at points A and C from the table, we find that the total head at point B equals 4.84 meters plus 0.937 times x in meters. In the problem statement, we were given that the measured seepage velocity, v, downward through the soil is 0.2 meters cubed per day per meter squared, or more simply, 0.2 meters per day. This seepage velocity is equal to the hydraulic conductivity times the gradient in the direction of flow. If we evaluate BC, we can make a couple substitutions and solve for the depth of water, x, explicitly. After converting the units and a little algebra, we find that the depth of water, x, is 4.81 meters. Plugging in this value to our previously derived equation for the total head at B, we find the total head at point B to be 9.35 meters. If we return to our table of pressures, we identified the total head at point B as equivalent to 3 meters plus the pressure head at point B. If we plug in our value for the total head, we find the pressure head at point B equals 6.35 meters. To find the pore water pressure at point B, we multiply the pressure head at point B by the density of water and gravitational acceleration, to find the pore water pressure at point B to be equal to 62.3 kilopascals. When compared with our possible solutions, the answer is B.